All right, so this right here is homework 13 on energy and momentum. So the first 7 questions are about energy, and mainly the main thing that we're going to be using is this equation right here. And that equation is the principle of work and energy. So the first problem, we start off with a bucket full of ore that is suspended from a Chamberlain crane that moves along a stationary bridge. So we're given the velocity, and it wants us to determine the maximum horizontal distance through which the bucket will swing. So right here I have just how it looks when it's at rest, and then right here's where once it swings. And then this length right here is the length of this once it's like at an angle. So this is actually the whole length minus this h right here. So that's how I have it, 30 minus h. And then this is what we're looking for, the horizontal distance, and we use the formula, which was the hypotenuse equals y squared plus b squared plus d squared, the square root of y squared plus d squared. But once we solve for d, we're given the square root of the 30 squared minus y squared. So this has to be squared right here. All right, so first to use this equation, we need to figure out the kinetic energy at point 1. And point 1 is actually when it's just here, and we're given the 1/2 times mass times velocity squared. That's what the kinetic energy is equal to. And then we're also wanted to solve for this right here, the work of the weight, which is negative mass times gravity times the h right here, the height. So, and then once at right here, the kinetic energy here will be 0 because there's no longer, or no, I believe the velocity will be 0 right here because that's the point we're trying to look for. Right, so then we plug in all of these into this equation. We're given this right here. We solve for h, and that's where we're given. Now that we have h, we can find y, and with y we can find for d. So we solve for y, which is right here, and then we solve for d, which is the horizontal distance, and it's given 9.53 feet. All right, and then problem 2, we are given a trailer truck that's being carried by a cab, and it wants us to determine the average force of the wheels of the cab. So then right here I just converted the velocity into units of meters per second. Then we have a free body diagram right here. We have this equation, sorry, I'm having a brain fart right now, the energy equation, to figure out our problem. So the principle of work and energy equation. So we do at 1.1 is when is 1/2 times the mass of both the trailer and the cab times the velocity at 1, which is given to us in the problem statement. We're given this. We do the same with 2, the kinetic energy at 2.2. We use the velocity that's given to us, and we get this right here. And then for the u, do the same as minus m times g times h plus f times d, because there's also a force going onto it. So, you know, we know what the mass is. Gravity is 9.81. We know what h is because it's a 2% uphill grade, and it's also a 300 meter distance. So this is why we multiply it 0.02 times 300. Then again, our distance was 300, so now we're solving for f. And then we plug in our t1, t2, and u1 to 2 to this equation to figure out our f. and that's what we get right here. And then for part B, it wants us to find the average force and the coupling between the cab and the trailer. So it's really this space right here. So I paid attention to just the trailer, and then right here is the weight of the trailer and then the force from the coupling. So again, we use the T1 and T are kinetic energies, but this time we're only keeping account the weight of the trailer, because that's what the force is acting on. It's on the weight. It's going to be pulling that weight right here. So we do it with the velocity at 0.1 and the velocity at 0.2. We're given this right here, and then the same thing as before. Our work and energy. Oh, sorry, no. Our work of the weight. It's the same as up here, the M minus mgh plus fd, but this time we're only keeping account the weight of the trailer, and then this is what we end up with. We plug all of these into the equation, and we figure out, we solve for the force of the cab, and that's what we end up getting. All right, so problem 3. This one is about the subway train. There's three cars of the subway, and it wants us to determine the distance required to bring the train to a stop and the force in each coupling. So what I did first is just figure out the kinetic energies and the work of the weight. So this would help me get the distance required to bring the train to a stop. So right here for the kinetic energy at 0.1, it's going to be the 1/2, and then the mass of all the trains from train A, train B, train C over 32.2, which is the gravity, because it gives us the weight and we only want the mass, so that's why we divided by 32.2. The velocity is given, so it's times velocity squared. This is what we get right here. And the work of the weight is negative force times d. And then we're also given the kinetic friction. So we could simplify the force by kinetic friction times newtons. They also give us the newtons, so we multiply that to get our force. And then also the kinetic energy at 2, the velocity will be 0, because that's when it will be at rest once it stops. So we plug that all into this equation right here, and then we just solve for the distance, which is 279.15. All right, and then the second part of this problem is the force in each coupling. So there's a coupling between the trains at A and B, and the trains between B and C. So this one's from A and B. So this is the train, this is train A. This is train C. So here we have the weight of the train, the force of train A, and then we're trying to figure out the force right here, A and B. So we have this equation right here. We know that the kinetic energy will be 0. So we solved for the kinetic energy at 0.1. Keep account only the weight of the train A times the velocity that's given. This is what we end up getting for our kinetic energy at 0.1. And then the work of the weight, again, we already have the force. So we plug it in. No, sorry, we don't have the force. We're keeping account. The force is this plus this right here, what we're trying to look for. So it'll be 28 plus FAB times the distance. This is what we have. This is what we solved right here. So it's 279. And this is what we're given. We plug this into this equation here, along with the kinetic energy at 0.1. This is what we have. And then we just solve for FAB. And then I ended up getting a negative 19.38, so that'll mean that's in compression. All right, so the same thing is for train C, and then also the kinetic energy at point 2 will be 0. Or here, when you keep account the weight of the train C, which will be 80 divided by the gravity, because we only want the mass. This is what we're given. And then this one right here, the work of the weight, we don't keep, unlike before, we had to keep in account this force right here, not for this one, because we only have one force acting on this train. So we only do negative F, the force that we want to solve for, times the distance, which will be solved in part A. Plug that into the equation, and then we're given this for our force, 8.62 kips. Sorry. And then for problem 4, we're given a guy that's he swings a rope, and we're trying to figure out the angle in which the rope will break, knowing that it could withstand a maximum tension equal twice the weight of the spear. And at the end of the rope there's a spear, so this right here is 0.1, is 0.2. So the 0.1 is when the person's about to throw it, and then right here is when we believe it will start to break. So we want to figure out the length of this. So we know that it's 2 meters times the sine of the angle, just because right here, just by trigonometry, this right here will be the sine. Again, we're going to be using this equation. So at T1, we know that we don't know the mass yet, but we do know the velocity, which is 5. So it's 5 squared, which will equal to 2.5 meters. At point 2, we do not know the mass or the velocity, so we're just going to keep it at this. And then for this one, for U, normally the formula is mass times gravity times the height. This we know, we saw it earlier with this, we decided earlier this would be the height. So it's mass times G times 2 times sine of the angle. Plug that back into this equation. This is what we're given, and then we want to solve for V squared, just because what we're going to do earlier, we're also solving for V squared, and we just set these 2 equations equal to each other to find the angle. So right here, we draw a free body diagram at point 2, and we have like this angle being the positive direction, and it's equal to m mass times acceleration. This is just a refresher from homework chapter 12, the last homework assignment we did. So the acceleration will be equal to V squared over the length, which is 2. And then once we take all the sum forces in the x direction, which will be this, like a little slanted, it's 2mg minus mg sine of the angle, and it's equal to m v squared over 2, which is this right here. And then again, we get v squared by itself, and this is what we're given. Set these 2 equal to each other, which is what we did right here, and try to solve for the angle. Try to solve for sine the angle, which we get the 0.2419. And then we just solve for the angle by getting the inverse sine, which is 13.999, or you could just round up to 14 degrees. And then problem 5, this one's a pretty simple problem. It talks about a chairlift that transports 100 skiers per hour. And the mass of the skier is 70 kilograms and has an average speed. The lift has an average speed of 75 meters per minute. So it wants us to determine the average power required and the required capacity of the motor if the mechanical efficiency is 85%, and if 30% overload is to be required. So for the average power, this is the equation we're given. This could be simplified to newtons times m, the natural force times mass times gravity times h, the height. And we know that the time is 1 hour, since it could transport skiers per hour. So all of this is given to us in the problem statement. We have 1,000 right here, 70 kilograms for the mass, 9.81 for the gravity, and the height was 30 meters. And then I converted the hour to seconds just to cancel this out right here, and we end up getting that the average power is 57,225 watts. And then the other one wants us to find the max power, which will be the average power plus the average power if the 300% overload is to be allowed. So that's what this is right here. So we get the average power, and then this one we times it by 3 just because this simplifies to 3, and this is what we're given right here. And then that's for the max power, yes. So and then the motor capacity is the mass power over the mechanical efficiency, which is given to us, which is 85%. Solve for it, and we get 269,294 watts. All right, so for problem 6, this one we're given a collar that's attached to a spring and slides without friction in a vertical plane along a curved rod. It wants us to figure out the velocity as it passes from point, here I have the picture right here, the velocity as it passes through point B right here, and as it reaches point C. So again, this is the equations I'm gonna be using. This is for the gravitational potential energies. No, this is for the potential energies for the springs right here. Yes. So it's 1/2 times k times x squared. This one is for the gravitational potential energies. And then these are the same equations we were using earlier. This one right here, except for this one right here. This is one new one. This one is the conservation of energy. So yeah, so then we could solve for it at point A, the kinetic energy, which is 0 since it's at rest, so the velocity will be 0. Then we figure out the potential energies for the springs. We're given we're given the constant, which is 600, and then x right here, this one's the elongation, which is we solve for it from the figure right here. We did 250 minus 150, convert it to meters, and then we square it, which is 3 joules. All right, and then right here we solve for the kinetic energies at B. We're given a mass, and this time we're not given a velocity, but we could solve for it. It's not 0 because it's not at rest, so the 2's cancel out. So the kinetic energy is only equal to the velocity. And the same with C, the kinetic energy will be equal to the velocity at that point squared. And then for the potential energies for the strings at point B, same thing, just different elongations because it's at different distance. We get 0.75 joules. The same for point C, the potential energies of the spring. This one right here, this cancels out, 150 minus 150, so it will be 0 joules. And then for the gravitational potential energies for point A and C, those will be 0 just because it's at the 0 datum level. So here you got A and C, this is the datum and it's at that level, so that's why it will be 0. while B actually has a value because it's not that it has a lower elevation, a lower height. So yeah, and then yeah, we saw for the gravitational potential energy at point B, which will be this equation right here. We have the mass, the gravity, and then the height right here, which is 200 millimeters. Convert that to meters, and we get negative 3.924 joules. All right, and then we go back to this equation to solve for the velocity as it passes through B. So it's TA plus VA plus TB, and then all the velocities that we have. So essentially the potential energy for the spring and the gravitational and potential energy will equal to the total velocity of point B. No, the total energy of point B. So we plug in all the values that we know right here. We know that TB was equal to the velocity V squared. Get that by itself and then square root this value to get the actual velocity of B. It's 2.48 meters per second. And then we do the same thing for point C. But plug in its energies that it has. Did not have any. The only value that we had was the energy at A and the kinetic energy for T at point. The kinetic energy at point C, which was just the velocity squared, square root 3, and we get 1.73 meters per second for the velocity at point C. All right, so then for problem 7, we're given this little figure. I actually drew a picture right here that a spring is used to stop a 50 kilogram package, which is moving down at an angle of 20 degrees, an incline of 20 degrees. The spring has a constant of 30 kilonewtons per meter, which I actually converted to newtons per meter. So again, we find the kinetic energy at point A, which is up here, which is 1/2 times the mass of the package times the velocity squared, which is like 100 joules. And then we're figuring out the gravitational energy, which is the mass times the gravity times the height. Since there's an incline, it will be the sine of 20 degrees. So we get 1,342.09 joules. And then we get the other energy, which is the potential energy for the springs with the elongation. So we're given this value right here in millimeters, which is converted to meters to satisfy this right here. Convert this to newtons just so we have everything in joules, and then we have 37.5 joules. And then once it gets here, once the string stops it, that's 0.2, and the velocity will be 0. So the potential energy, the kinetic energy here will be 0. And then at 0.2, the gravitational energy. The only difference here is that it'll be negative just because it'll be lower, and then we don't know how far down it'll be, so that's why I have an x. So I get negative 167.76 x. And then for this one right here, same thing. I added x to it just because there's more to it, because it goes down lower with the spring. And I'm actually given this right here. And then plug this in this equation right here, plug in all the values I know. I'm given this right here, plug that into the quadratic formula, positive and negative value. We're gonna go with the positive one, and we get 0.269 meters for the maximum additional deformation of the spring and bringing the package to rest. So that concludes the energy portion of the homework. Now we have the momentum portion. So kind of like similar concepts, but just use different equations. I know we use a lot of this equation here. and we apply the impulse and momentum principle. So first, the problem statement is that steep safety ramps are built to maintain higher weights to enable vehicles with effective brakes to stop. And then we have a 10-ton truck that enters a 15-degree ramp at an initial velocity of 108 feet per second and travels 6 seconds before its speed reduced to 36 feet per second. So we're assuming constant deceleration and wants us to determine the magnitude of the braking force and the additional time required for the truck to stop. All right, so we got our free body diagram here. Oh, well, first we're given the weight of the truck, which is 10 tons, current at 2 pounds. But we need the mass for the equations that we're going to use. So divided by 32.2, so we get 621.118. Yeah, for our mass. And then the impulse and momentum principle is the mass of the truck times the initial velocity plus the impulse, which equals to the mass of the truck still with its the velocity that it was reduced to. And then we get the impulse by taking the sum of forces in the x direction, which is this right here, times the time. That's what the equation is. It multiplies it by the time. Plug the values into this equation. We know that the only thing that's left to solve is for the force. And for the force, we get 2,277 pounds. And then to find the additional time required for the truck to stop, do the same thing as up here. The only difference is that the velocity will be 0 since it's at rest. So this will be 0, this whole thing. That's why I set it to 0. We know the force already. We can plug in the force. We just got to figure out the time, which is here. Solve for the time. We get 9 seconds. It wants us to find the additional time that it requires. So we do 9 minus 6, which is the speed it travels before it reduces to a different velocity. And we'll get 3 seconds. So this is the additional time that is required. All right, this one we're given a system, this system right here. Just from looking at it, we can see that the velocity at the cube at A is 2 times of the velocity at point B. And by doing that, we know that the velocity at B is half of the velocity at A. So same thing as the last problem. Get the sum of forces in the x direction. I did the positive going this way over here. So you get 150 newtons minus 2t, 2 tensions. So this will be our impulse times time. But that's the mass. So we're only focused on B now because it wants us to find the time in which the velocity at color B will be 2.5 meters per second to the left. So that's why for part A we're only focusing on block B. Again, like the other equation, this is the mass of B, and then VB at 0.1 when it's at rest, so it'll be 0, and then 0.2 is when it's equal to 2.5 m over s. The velocity is equal to that. So plug in the values. We do know we're given this value right here, 150t minus 2 tension times the time equals 20. And then we take the sum forces in the y direction for block A, which we're given this right here, t minus 29.4t, because it was t minus mass times gravity. The mass was 3, gravity 9.81, so we're given this value right here, and this will be our impulse times t. Again, the velocity at rest will be 0. Plug in the impulse, and then we know the velocity of A is 2 times the velocity at B, so that's why it's 2 times 2.5. Got the mass of 0.8 of block A, which is 3 kilograms. simplify the best way we could, and this is what we get right here. And we notice a common oh sorry, no, this is what we get first. And we notice that this has a 2 tension times time, and this one just has tension times time, so we multiply it by 2. So we could add them together and cancel those out, so we're left with this, and we solve for the time, which is 0.549 seconds. Now point B wants us to find the corresponding tension in the cable, so we could go back to either one, this one right here or this one right here. I chose this one right here, what we solved for earlier. Plug in the T for the times because we know that already. Now we're just trying to solve for the tension, and then we get 56.80 newtons for the tension. All right, and then problem 10, we're given a ballistic pendulum, and it's used to measure the speed of high-speed projectiles. So really is a bullet that goes through here, a 6-gram bullet that's fired into a 1-kilogram block of wood, and it's suspended up right here. So this is kind of similar to the first problem we did, but again, this one is asking us to find the initial speed of the bullet, so right when it was fired, the impulse parted by the bullet on the block, and also the force of the cord immediately after the impact. So yeah, so we're given this right here. Just from the figure right here, I was able to figure out the height from here. This is really like the H, just didn't write it, but this was the H right here. All right, so we know the cord, the length of the cord which is given to us, which is 22.2 meters. We know the angle, so this length of the cord right here, once it's suspended up, is 2.2 times the cosine of 60. But we're also interested in H, so it'll be 2.2 this right here minus this right here, which are given 1.1 meters. So the energy, the gravitational energy will be m times g times h, which we know our h, which is 1.1 meters, and our kinetic energy, which will be 1/2 times mass times velocity squared. And then we set them equal to each other to figure out the velocity, which we could just plug in all the values. The only thing we don't know is the mass, but those could cancel out. Solve for the velocity, and we're getting 4.65 meters per second. And then to figure out the initial velocity, we applied the conservation of momentum principle, which was what we've been using. It's the mass of the bullet times its initial velocity plus the mass of the block times its initial velocity. And then this one right here at the end is equal to the total mass of the bullet and the block times its velocity after the impact. So we know the mass of the block, we don't know the initial velocity, that's what we're looking for. And then the block, its initial velocity is when it's at rest, so it's 0. And then the mass of both the block and the bullet is just 1 plus 0.006 kilograms. It's given this right here. And then the velocity is what we solved for earlier. We just solved for the initial velocity right here, and we're given 779.65 meters per second. And this one right here, we apply the impulse momentum principle to find the impulse imparted by the bullet. So again, this one uses the same thing. Oh, sorry, I'm looking at the wrong one. Yeah, so this is what we're trying to look for right here. So again, we only keep this right here is the mass of the bullet, and this right here is the initial velocity of the bullet, which we solved for earlier. And right here will be the mass of the bullet as well, with the velocity that after the impact. So solve for plug in all the values. Sorry, we plug on all of these values, solve for F, and we get 4.65 joules. Sorry, this is FT, which stands for the impulse imparted by the bullet. And now it wants us to find the force of the cord immediately after the impact. So this right here, take directions, and we take the sum of forces in the y directions, which will equal to mass times acceleration. We know that we have the force of it going up and the force of it going down, and then it's equal to, the velocity is also equal to v squared over the length of the core, which is 2.2. Just put F by itself. We know the mass. It's asking us for immediately after the impact, so that will be the mass of both the bullet and the block. Plug those values in, and the gravity, and we're given 19.76 newtons. All right, and then problem 11. This one was kind of tricky. I'll show you right here. We're given this figure as a problem statement right here. How this initial velocity is going to knock on both of them, and it wants us to determine the velocities of A and B immediately after the first collision from this right here. So we know that the masses of all three of them would be equal to each other, so M would just equal to the mass of all of them. So again, this probably the same formula as before. The mass of ball 1 times its velocity is initial velocity. The mass of point B, ball B, times its initial velocity. And then this one is this velocity 1 right here, its velocity immediately after the impact, and that's also for B. All right, so we know that A will have an initial velocity after it's hit by this right here, so this is why we have that. B won't have one yet because it'll still be at rest, so it'll be 0, because immediately after it's hit, this will have a 0. And then we're trying to find the velocity of these once it's hit and it hits against each other. So we simplify the initial velocity to get this equation right here, and then we can also simplify some more to get VB equals the initial velocity minus VA1. And then right here we're trying to find for the relative velocities. It's given by this equation right here. We try to get E by itself, and this is what we ended up with. After more simplifying, we ended up with this right here. And then, we simplify it, and then we end up with this right here. And then, like earlier, we have VB, which is equal to this right here. Plug that into here. Now we could solve for VA, the velocity of A immediately after the first collision. So plug that in, solve for VA. It's given to us like this. And then earlier right here, what we did was get VB by itself. Now we do the same with VA, get VA by itself, plug that into this equation right here, given this, and then solve for VB on its own. We're given this right here. And then we do the same thing for B. So yeah, these are the velocities of A and B immediately after the first collision. And now part B is asking us to find the velocities of B and C immediately after the second collision. So that's why we have ball B with its velocity after the first collisions plus MC and its velocity. Its velocity after the first collision will be 0, just because it'll be immediately after. It won't have time to hit this yet. And then it's equal to MB times VB 2, which that will be the velocity after a second collision. And then after a second collision, that's when BC will have a velocity, which will be BC1. All right, so yeah, that's when we figure this out. This would just be M. We know what VB is because we saw the earlier. Plug that in. We know the velocity of VC will be 0 because it'll be at rest. And then the rest of this we don't know, but we could solve for. And then again, what I did here is try to get V1C by itself, which is this is how I simplified it with. So, and then later when we saw for the velocity of B after second collision, we will set B by itself. But right now we're just focusing on the first velocity of C after the second velocity of C. Again, we do the relative velocities, which was simplified to this right here. And then I get V1C by itself, plug that, no, set these two equal to each other, and then could simplify that to this right here. Then we simplify it to get the V2B, to get the velocities of B after second collision, which is this. And then just like the other problem, the previous problem, you know how we saw a pattern here? It's 1 minus E, and then when we minus this, when we got A by itself, almost the same thing, just except the E was positive this time. And then the same principle applies to here. When we solve for C, the E is positive. So I noticed that pattern from this problem. Notice this, it will be the same for this one, and the work is right here. Yeah, that's our two velocities. Now for problem B, no, sorry, problem 12. Same similar problem as the other ones. You know, we're given a sphere here, a block's hitting it, and it's like gets to a certain height, and it wants us to figure out the maximum height reached by the sphere and the distance traveled by the blocks once it hits the sphere. So use this equation right here. The initial velocities plus, so the initial velocities plus each other, and then plus the velocities after the collision. So we know for the sphere, the velocity was 0 because it's at rest. The initial velocity of VB of the block was 2. Yeah. And then we're trying to solve for the velocities after the collision. So we simplify it, and then we get this right here. So V1A plus 2 times V1B equal 4. And again, we get the relative velocities. And then we're already given the E in the problem statement. So this could help us solve for this right here. And just like the previous problem, I'm gonna just set V1B equal to itself, which is negative 1.6 plus V1A. Plug that into this equation right here, and then that could help me solve for V1A. And then once I have V1A, I could plug that into this equation to get V1B, which is I did and got this right here. And this is a quick sketch of the system. We could solve for the kinetic energies of 0.1. This one has an initial velocity of 2.4, which we're given right here. No, sorry, it's not the initial velocity, it's once the hit happens. And then we're trying to find the maximum height right here, so the velocity will have to be 0. And then the energy at 2 right here, it's also given by the equation of mass times gravity times height. We don't know what height is, that's what we're trying to figure out. Here, the energy at 1 will be 0 because the height will be 0 because it's at the datum level. And then we have this equation right here, T1 plus V1 equals T2 plus V2. Plug in the values that we just solved for right here, and then get H by itself, and we get the max height to the sphere will reach, which is 0.294 meters. Now it wants us to find the distance traveled by the block. So we're focusing on the block now. So the kinetic energy for the block, this is the mass 1, and this is the velocity 0.8. So it's given right here. And then we're given this in joules. Again, want to find the distance. So 0.2 will be once it's at rest. And then we use this right here to figure out the distance, which is negative force times the distance. We're given the friction factor, so we could solve force this by this way. And then this, the natural force, could also be simplified to mass times gravity. Plug in the values we do know, we get negative 5.886 D for the work of the weight. Plug in the values back in this from the energy homework that we just did for the first 7 problems. And then, yeah, we know that T20, we know the values for these, plug them in, trying to find the distance, solve for it. And we get 0.0544 meters. And so it could look a little bit nicer, converted to millimeters. And this is what we get for the distance, 54.4 millimeters. And that concludes homework 13.